In the last two videos, we've dealt with vectors in 2 dimensions. We're going to now look at vectors in 3 dimensions. As you know, our world isn't flat, so we need to be able to think about the third dimension. And to do this, we need to bring in a third coordinate, which for the purposes that we're going to be using, we need to assign a letter to it. So here's our 2-dimensional vector stuck in a page. We need to bring it out of the page in order to be able to make it a 3-dimensional vector, and we add to the components I and j a third dimension, which is the letter k. In terms of axes, we bring in a third axis, so I now deal not just with the x, y, and z xy axes, I also deal with the x, y, and z axis. If we look at it in terms of a diagram, this is what we're going to get over here. Here is my x-axis going along the bottom horizontally, going in that red direction there. The y-axis is going up along the page, into the page, and the z-axis is the one that goes vertically up. And so there I have my position vector for the point A. X, y, and z in column format. So if I have a point that's defined by the coordinates 2, 3, and 4, the position vector is going to be 2 along the horizontal axis, 4 up the y-axis, and then 3 up the y-axis, and then 4 out of the page, and that gives me my position. A vector 2, 3, 4 is a free vector. It's going to be anywhere on that page basically. It could be there, it could be there, it could be there. But a position vector, remember, is a vector that's linked down to the origin. There's only one place for that position vector. We have a shape in 3 dimensions, a cuboid, so a 3-dimensional rectangle, and they give us some coordinates. A is the point 1, 0, 0, so it's 1 along the x-axis, nothing along the y, nothing along the z. G up here is the point 1, 4, 2. So to get to the point G, what I've done is I've gone 1 along the x-axis, I've gone 4 down the y-axis, and I've gone 2 up the z-axis. That gives me my point G. So any point that's up here, H, E, and F, will all have a z component of 2. Any point along here, so B, C, F, and G, they're all going to have a y component of 4 because they're 4 away along the y-axis. Any point along this line over here is going to have an x-coordinate of 1. So A, H, G, and B all have an x-coordinate of 1. We can see that over there. E, we're told, is the point 6, 2, 6, 0, 2. So what's happened here, it means I've gone 6 along the x-axis. So any point along here, D, C, F, and E, they're all going to have an x component of 6. E has a y component of 0. So in other words, it hasn't moved along the y-axis. So D, E, H, and A all have a y component of 0. And E has a z component of 2. So in other words, it's moved up 2 places along the z-axis, as has the point H, G, and F. So that's how I'd go about fixing the coordinates of those particular points. So I now need to find the position vector for A. Well, we got A as being 1, 0, 0. We have F as being the point 6, 4, and 2. Stop the video and figure that out if it's not immediately obvious to you. So if I want to find the displacement vector AF, AF is simply going to be little f minus little a, plug in the values, the displacement, the position vectors that I have for those 2 vectors, simplify, and there's my displacement vector AF. To get the vector DG, I need to know the coordinates of D, and I need to know the coordinates of G. So there's the displacement vector DG. That's going to be little g minus little d. There are the 2 position vectors for G and D. And if I subtract them, I get my displacement vector dg as being minus 5, 4, and 2. If I want to get the magnitude of that, I simply need to take those coordinates and plug them into the Pythagoras formula. And there I get my displacement of 6.71 units. There's some questions relating to three-dimensional vectors. So I've got the position vector for P as being 2i plus 5j minus 3k, q as being 3i minus 2j plus 5k, and I want to find these particular value solutions over here. So to find 2p plus q, all I have to do is basically plug in my position vectors into that formula, multiply out, collect like terms, and there is my solution. If I want to find the magnitude of PQ, then, we could also do that in column vectors, and we'd come up with the same solutions. If I want to find PQ, remember PQ as a displacement vector. The displacement vector is made by taking the position vector of Q and from it subtracting the position vector of P. So using column format, I can just plug those things in, and there I get my displacement vector 1 minus 7, 8. Having got the displacement vector, I just plug it into the formula, and I'm able to get my my magnitude as being the square root of 114. The unit vector in the direction of Q, well, in order to get that, I need to take the position vector of Q and the magnitude of Q. And there we have the unit vector in direction of Q. If we want to see if lines are parallel, well, we need to look at the various vectors. So if we take vector B, the position vector B, if you notice the coordinates of all the components I, j, and k are multiples of 3, so I can extract 3 as a common factor. And if I do that, hopefully you can see this vector over here is the same as that vector over there. So in other words, I can write that as 3a, which means that a and b are parallel to one another. If I go and take vector C, I've got a whole lot of fractions involved in this, so in order to get rid of the fractions, I'm going to multiply everything by 2. I've also got a whole lot of minus signs in there, so I'm going to multiply by minus 2. And so I come up with this statement over here. Now this looks fairly similar to vector A in the sense that the I component is the same, the J component is the same. However, the K component isn't. Here we have minus 3, here we have plus 3. So that tells me that these two vectors, C and A, are not parallel. And if C is not parallel to A, it also won't be parallel to B. Now, here I've got a diagram with two position vectors for the point A and the point B relative to the origin. So, if I want to find the displacement vector AB, I can say that it's going to be AO, or minus OA, plus OB. There is my displacement vector AB. Now, M is the midpoint of this point line AB. And I want to find the position of the point M, the position vector. Now, OM, this position vector over here, is simply going to be OA plus AM. And AM is a half of AB. So if I know my displacement vector for AB, and I know my position vector for OA and my displacement vector for AB, I can plug those in. I come up with this formula over here. And there I get the midpoint of the line AB. Now, I wouldn't suggest that you try and remember that off by heart. I think it's possibly better to do all of these problems by looking at a diagram and working with the various vectors that we have here. So let's say that A is the position vector 2, 1, minus 3. B is the position vector 4, 6, 3. I want to find the midpoint of the displacement vector AB. All I have to do is plug the values in, and there is my displacement, my position vector for the point M. Now, ABC is a parallelogram. We have position vectors for the points A, B, C, and D. M is the midpoint of CD, and N is a point on BC such that the ratio of BN to NC is 1 to 3. Find the position vectors of M and N, and find the displacement vector Mn. Now, with all these sorts of problems, it's difficult just to try and do all of that in your head. So first thing, always a good idea to draw a diagram. We have O as our origin because we're dealing with position vectors. We have M on the midpoint of CD, and we have N on the line BC. Now, this one's quite simple to get. If it's a midpoint, I know that DM is going to be half of DC. The ratio that I'm given over here, that BN to NC, is 1 to 3, means that the line that BN is going to be a quarter of this full line. Why it's a quarter, not a third, is because if that's 1 and that's 3, in order to get my ratio of 1 to 3, the full line BC is going to be at least 4 units long. And so BN will be a quarter of the line BC. So in order to find OM, I'm going to say it's OD, that position vector, and then the displacement vector DM, which is a half of DC. And if I put all that together, I get my position vector for M. N, as we said earlier, is going to be a quarter of the way along BC. So I'm going to get that ON is going to be OB plus a quarter BC. Plug all of that in, and there I get my position vector for ON. Finally, if I want to get the displacement vector MN, all I have to do is plug those values in, and there is my displacement vector. Generalize all that we've done there. If we've got two position vectors, A, which has the components x1, y1, z1, B, the x2, y2, z2, then the displacement vector AB is going to be little b minus little a, position vector B minus position vector of A, and I simply subtract the different component parts. Likewise, if I want to find the length of AB, the magnitude of AB, I'm going to plug those differences into the Pythagorean formula in order to get my displacement. So here we've got 2 points, A and B, and I want to find the distance between the 2 points. So first of all, I need to find the displacement vector AB. Now the displacement vector AB is going to be position vector B minus position vector A. So I plug those two values in, they've given them to me, and I come up with the displacement vector for AB as being 3 minus 1 minus 3. The magnitude of AB then is just plugging those values into the Pythagorean formula, and here I have my value of AB as being the square root of 19 units. Note I keep it in surd form in order to keep it more accurate and more precise. Different problem says this: the points P and Q have position vectors given by 1, 2, 5 for P and 5, 2, minus 3 for Q. Point N divides PQ so that PN is a quarter of PQ. Find the distance of N from the origin. Now, as we said before, try and draw a diagram to represent this. There are my 2 points P and Q. There's my displacement vector PQ, and N lies along it, so it's a quarter of the way along PQ. So if I want to get my position vector for N, it's going to be OP plus PN. Pn is a quarter of that full length, so all I have to do is then plug in the values that I have for that. It's going to be position vector P plus a quarter of Q minus P. I plug those values in, and I get my position vector for N as being 2, 2, and 3. Having got my position vector for N, all I then need to do is go and plug that into the Pythagorean formula, and I'm going to get that the distance of N from the origin is going to be root 17 units. Finally, I have coordinates for the point A as 2, 1, minus 3, and B is 0, minus 1, 4. I need to find the position vectors of C, which is the midpoint of AB, and the position vector of the point D, which divides AB in the ratio 1 to 3. So as always, draw a diagram. We know that C is the midpoint, so I need to find the displacement vector AB. I've got the two position vectors for that, so that shouldn't be a problem. There's my displacement vector AB. Now, if I want to find the position of the midpoint, the position of C, we know that AC is a half of AB, and I can get that vector by plugging the values in. So if I want my position of C, I know that OC is going to be OA plus AC. Plug in my values. There is my position vector for the point C. Now for the second part of the question, we want the point D, which divides AB in the ratio 1 to 3. Again, we've got our diagram. D is dividing this in the ratio 1 part over here, 3 parts over there. So as we saw in a previous example, AD is going to be a quarter of the line AB. So if I want to get the position vector OD, it's going to be the position vector of A, so OA, plus the displacement vector AD, which is a quarter of the vector AB. So plugging all those values in, I'm now going to get my position vector for the point D as being 1.5, 0.5, and minus 1.25. Right, what you need to do now is go and find the homework exercise on my iMaths for three-dimensional vectors and work on that, please. Thanks very much.